Alright, so in this section we're going to begin exploring trig integrals. And what I have listed up here are some essential formulas. So this we should already have memorized, right? That should be automatic. And then these two just come from adding or subtracting cosine to the other side. Right? So you could say that these three formulas are kind of all the same. Then we can look at this formula. So this formula we can prove with trig. But it may be better for you to just get these written down on flashcards. So maybe you write something like tan squared of x plus 1 on one side, and then secant squared of x on the other side of the flashcard. And you should be able to look at either side of that flashcard and know what's on the other side. So these two orange ones are basically the same formula. We're just moving one to the right-hand side or left-hand side. Then we have this formula, which basically just comes from flip-flopping sine and cosine from the orange formula. So these two purple formulas are going to be analogous to each other. And then we have these two special guys down here, which I don't know if you've seen these before. But we are going to use these quite frequently. If not in 7.2, then in 7.3 for sure. This one right here comes from U substitution. Right, this is something we should already be able to do. And then this one right here, we will prove later today or tomorrow whenever 7.3 drops. But it's okay in the meantime if you want to use it on homework, quizzes, or the exam. You can use this if need be. Just a reminder, so this is 7.2. After this material, we will have covered everything you need for the exam on Friday. Also, a reminder to show up 30 minutes before the exam. Right, so class starts at 10. You should show up at 9:30 to make sure you get checked in time to start the exam on time. Starting late because you didn't show up early or you showed up late is going to be on you. Okay, and then these down here, so these are just some formulas that make our lives easier, but we can get by without memorizing them. So I want to point out this one right here. Here we go. At the end of the last section, we did a integration by parts problem, which was a loop. And I believe it was something like the integral of sine of 2x, cosine of 3x. If we had broken it up using this formula, it would have been a whole lot faster, a whole lot easier. We could have just done it with U sub. But that's no fun, right? So we did the loop. Alright, so our goal with trig integrals is to get our integral to look like the form in part 1 or part 2, and then use the necessary case A, B, or C. What I mean by that is part 1 of these notes are going to contain integrals that look like this right here, where it's going to be sine times cosine. Let me get the whole thing in there. Where it's going to be some power of sine times some power of cosine dx. And then our cases A, B, and C, we'll know whether to use A, B, or C depending on whether these powers are odd or even. And then part 2, we'll look at something that looks a little bit different from that. And again, we'll be able to break it down into cases depending upon whether our powers are odd or even. So let's go ahead and get started. Let's look at this first one. This first one says, if n is an odd number, use cosine squared of x equals sine squared of x minus 1, and u equals sine of x. So basically what this is saying is that if we have something like sine to some power times cosine to some power, if cosine has an odd power, then what we'll want to do is we'll want to rewrite cosine squared of x equals sine squared of x minus 1. And the way we're going to do that is that we're first going to break this apart a little bit. So what I'm going to do is we'll keep sine the same. I'm not going to mess with it. But cosine to the fifth of x, I'm going to rewrite this as cosine to the fourth of x times cosine of x, right? Right now, we should be thinking that I'm just doing witchcraft for no apparent reason. But we're going to see the reason here in a couple seconds. So we'll have sine to the sixth of x. Now, cosine to the fourth of x, that'd be the same thing as saying cosine squared of x squared, right? Because we just multiply these exponents right here. And we get 2 times 2 will give us 4, which was the exponent we had up here, if I wrote a 4 up here, and not just like whatever that was. And then we'll have this cosine x dx right here. Now here's what we're going to do. So this case, we had an odd power of cosine, so we broke cosine up. And the way you break it up is you just pull out one of the factors of cosine, to where cosine now has an even power. Then what you do is you take that even power and you write it as cosine squared to some power. Right, so here we had cosine squared to the second power, because 2 times 2 gives us that 4 that we had up here. Okay, and so now what I'm going to do is I'm going to take that cosine squared and I'm going to rewrite it as sine squared of x minus 1. So we'll have sine to the sixth of x times, now I'm replacing that cosine squared of x with sine squared of x minus 1 squared. And then we'll have our cosine x dx. Okay, so going over the steps again, we have odd power for cosine. We factor out one of them. We rewrite the cosine with the even power using sine squared of x minus 1. Now what we're going to do is we're going to do u substitution. The way we do our u substitution is we use u equals cosine of x, which means that du over negative sine of x will be equal to dx. So then this becomes the integral of, I'm sorry about this. We should be using u equals sine of x. Whoops. And so hopefully here in a couple seconds you'll see why I figured that out so quickly. The reason we're choosing u equals sine of x is because I want this right here to cancel out this cosine of x. So let's see how that happens. So we get sine to the sixth of x. Well, let's see, u was sine of x, so I'm going to go ahead and rewrite this as u to the sixth. So this is u to the sixth. Then I had sine squared of x, so it's going to be u squared minus 1 squared. And then we should have cosine x dx, but dx is equal to du over cosine x. And so now we can see where these cosine x's will cancel out when multiplied together. And so this is going to give me the integral of u to the sixth. Let's see, u squared minus 1 squared, that's going to be u to the fourth plus 1 minus 2u squared du. Now I'll multiply out that u to the sixth, so we should have the integral of u to the 10th plus u to the sixth minus 2u to the 8th du. And so now we'll go ahead and integrate that. So I'm going to have u to the 11th over 11 plus u to the 7th over 7 minus 2u to the 9th over 9 plus c. And now I'll go ahead and plug back in u equals sine of x. So this is sine to the 11th of x over 11 plus sine to the 7th of x over 7 minus 2 sine to the 9th of x over 9 plus c. Okay? And so this is how we deal with integrals of this form. Now let's go ahead and see an example where it's not so straightforward. What I mean by that is that this isn't so straightforward because, now it's not just like simple powers of cosine and sine. Now we've got this square root in there. But I'm still going to go ahead and use the same rule. I've got an odd power of cosine. So I'm going to break this up. This is going to be cosine to the fourth of x times cosine of x times, this is sine to the 1/2 of x dx. Now what I'm going to do is I'm going to use still u equals sine of x. And so I'm going to consolidate this kind of all into one step. So u equals sine of x du over cosine x equals dx. Now what I'm doing here is I'm rewriting this cosine to the fourth of x. Right, so we've got cosine squared of x squared. But remember, we're going to be rewriting this cosine squared of x as 1 minus sine squared. Right? So, let's see. So this is 1 minus sine squared of x. Which reminds me, okay, there's something sneaky I did up here. This right here is not correct. This should be 1 minus sine squared of x. The reason it doesn't matter is because we square this. So flipping the negative right there isn't going to matter. I need to make sure I stop doing that. Right? Y'all should get in the habit of just writing 1 minus sine squared every time. Don't do what I just did there because you need to be very careful about when that's going to work and when it's not going to work. Right? Meaning if I'm not raising it to an even power, then that negative is going to affect our answer. Okay. And then this 1 minus sine squared, so this was 1 minus u squared. Okay. Now let's get back to this problem. Okay. So I've got 1 minus sine squared of x squared. So that was our cosine to the fourth of x right there. And then I should have cosine of x times, let's see, we're doing u equals sine of x. So this is u to the 1/2. And then we should have a du over cosine of x. And since we're doing that u substitution, u equals sine of x, I'm going to go ahead and plug that in for this sine squared. So this becomes u squared. Make this look a little bit more normal. Okay, so then this is the integral of 1 minus u squared squared. Our cosines will cancel with each other. And so we'll have u to the 1/2 du. So then this becomes the integral of, let's see, this is 1 plus u squared minus 2u squared times u to the 1/2 du. And so now I'm going to multiply out this u to the 1/2. So we should have u to the 1/2 times 1 is u to the 1/2 plus, okay, u squared. 2 is the same thing as 4 over 2. So plus 1/2, that gives me u to the 5/2. And I've got 2u, and again, this is going to be, sorry, this should be just negative 2u. So then this should be 3/2 du. Okay, where I'm getting this from without like doing any foiling, right? If we're calculating 1 minus u squared squared, I like to think of this as a minus b squared. And so this is a squared plus b squared minus 2ab, right? So then I just replace everything. 1 u to the 4th, 2 times 1 times u squared. Or sorry, yep. And now we can see where the mistake's coming from, right? So it should be 1 plus u to the 4th minus 2u squared. Okay. So going back, 4 is the same thing as 8 over 2. And so 8 over 2 plus 1 over 2 will give me 9 over 2. And then this should be 5 over 2. Okay. And I need to make sure we keep our negative sign there. Alright, so that right there is an example of hopefully all the mistakes that can be made in this problem. Right? Just be careful with your foiling. Right? Be careful that we're keeping this power here, this u squared. We're not just treating it as u. And then just be careful about the signs, whether this is 1 minus u squared or 1 plus u squared, whatever it is. Okay, so then we'll get, let's see, we can actually start integrating this. So this becomes 2u to the 3 halves over 3 plus 2u to the 11 halves over 11 minus 2, oh, this is going to be annoying. So it's going to be 2 times 2 times u to the 7 halves over 7 plus c. Okay. And so now plugging in u equals sine of x. All of this over 2 nonsense in here, right? That just means that they're square roots. So I can go ahead and write that out. So this is going to be 2 square root sine cubed of x over 3 plus 2 square root sine to the 11th of x over 11 minus 4 square root sine to the 7th of x over 7 plus c. And so here is our final answer. Alright, so this should hopefully provide a pretty decent understanding of what we do whenever cosine has an odd power. Now, if sine has an odd power, right, so this is saying if m is an odd power, m is the power of sine, then we use sine squared of x equals cosine squared minus 1. And u equals cosine of x. Okay, I need to correct something. So this should be this right here. Remember, so the reason this isn't causing us a problem right now is because we're squaring it. But this should be 1 minus sine squared of x. And this right here, let me get rid of this so I can write it in. This should be 1 minus cosine squared of x. Let me draw this pretty bubble again. Okay. So if m has an odd power, then what we're going to do is we're going to kind of basically do the same thing we were doing to cosine, except for we're going to apply it to sine. Which means we're going to break sine down. We're going to use this trig sub, this sine squared equals 1 minus cosine squared. And then we'll use u equals cosine of x instead of u equals sine of x. Before we can do any of that to this problem, I want to make this look like sine to some power of x, or sine to some power of just a variable. I don't want a 10x in there. So what I'm going to do is I'm going to do our w substitution. So I'm going to do w equals 10x. So dw over 10 is equal to dx. So then this becomes the integral of sine cubed of w times dw over 10. So this is 1/10. Now I'm going to break up the sine cubed of w, so I'm going to write this as sine squared of w times sine of w dw. Okay, so then this becomes 1/10 times the integral of, so this sine squared of w, this should turn into a 1 minus cosine squared of w. So here's an example where if I didn't fix this part right here, we would get our answer probably wrong here because there's no squared here in this exponent. What I mean by that, right? There's not like this thing squared, right? So it's not going to cancel out that -1 that we're multiplying by to get the wrong answer up there for the trig sub. So this is 1 minus cosine squared of w times sine of w dw. All right, so then this becomes 1/10 times the integral. So now what we're going to do is we're going to use our u substitution. So let me actually fit our u substitution in over here. So I'll do, it says we're supposed to use u equals cosine of x. So what I'm going to do is I'm going to use u equals cosine of w. So u equals cosine of w, which means that du over negative sine of w is equal to dw. So then this becomes 1/10 times the integral of 1 minus u squared times sine of w, and then dw is du over negative sine of w. So I'm going to pull this negative out, so this will become a negative 1/10. And then we'll have the integral of just 1 minus u squared du. So then this is negative 1/10 times u minus u cubed over 3 plus c. So we make our first substitution, which is for u. U is equal to cosine of w. So this becomes negative 1/10 cosine of w minus cosine cubed of w over 3 plus c. Now we make our substitution for w, which was w equals 10x. So this becomes negative 1/10 cosine 10x minus cosine cubed 10x over 3 plus c. Okay, and so now we'll try another example of how we use this m having an odd power on what's going to be a definite integral. And a good thing to keep in mind, right, so look at this one right here. Cosine has an odd power and sine has an odd power. So I can use whichever one I want to. I can use the cosine rule or I can use the sine rule. I'm going to use the cosine rule because we don't get that negative, right? We end up using u equals sine of x, which means that our derivative is a positive cosine of x. So I don't have to worry about more negatives floating around. Okay, so I'm going to rewrite this as, it's still the integral from pi over 2 to 0, because I'm not doing any substitutions yet. So I'll have cosine squared of x, cosine of x, sine cubed of x, dx. Okay, then from here, now I'm going to work on my u substitution. So now I'm going to use my u equals sine of x, and we should have du over cosine of x equals dx. Now let me point something out here. Notice how we use u equals sine of x here. A good way to remember of what trig sub goes with what u substitution, if we're using u equals sine of x, that means I want to get as many sine of x's in here as I possibly can, which means I'm going to change this cosine squared of x into a 1 minus sine squared, right? Notice up here I did u equals cosine of w, which means I wanted to turn as many of these sines into cosines as I could. So I changed this sine squared of w into 1 minus cosine squared. Right, that's one way to remember if you're doing the right u sub with the right trig sub. Okay, so then this becomes, so a key thing here is that we remember to change our limits of integration. So we have u equals sine of x. So this upper limit should become sine of pi over 2, which is 1. And we should have sine of 0, which is 0. So this becomes 1 minus sine squared of x, right? That's coming from our cosine squared of x right here. And so this sine squared of x, this is going to be u squared. So let me narrow that down. 1 minus u squared. Then we should have a cosine x. And then sine cubed of x, so it's going to be u cubed. And then dx is du over cosine x. So this becomes the integral from 0 to 1 of 1 minus u squared. Our cosine x's cancel. And so then we just have u cubed du. So this is the integral from 0 to 1 of u cubed minus u to the 5th du. And so then this is going to be u to the 4th over 4 minus u to the 6th over 6 evaluated from 0 to 1. Let me clean up this fraction a little bit. U to the 6th over 6. Okay. When we plug in 0, everything becomes 0. So really all I'm calculating is 1/4 minus 1/6, which should give me a total of, so we'll have 6 over 24 minus 4 over 24. So this will be 2 over 24, which is equal to 1 over 12. Okay. So that's how we do one of these trig integrals when we actually have limits of integration and things to evaluate. Now we're going to look at the case that n and m are both even. If they're both even, then we have to use what's called the half-angle identities. The half-angle identities are going to be these right here. So these are the half-angle identities that I refer to. Okay, back to the problem at hand. Okay, so the first thing we do is we rewrite using these half-angle identities. So this becomes the integral of sine squared of x is going to be equal to 1/2 1 minus cosine 2x. And then cosine squared of x is going to be 1/2 1 plus cosine 2x dx. So what I'm going to do first is pull out this constant multiple of 1/4. So when I do that, we'll get 1/4 times the integral of, well, so we can look at this as like a minus b times a plus b. When we multiply stuff like this together, we get a squared minus b squared, where a is 1 and b is cosine of 2x. Okay, so then this is 1 minus cosine squared 2x dx. Now, here's an important thing. So our identity says that 1 minus cosine squared of x is equal to sine squared. I completely agree, that's true. A better way to think of this is that 1 minus cosine squared of some f of x, right, some function in here, is equal to sine squared of f of x. Okay, so that means that 1 minus cosine squared of 2x is going to be equal to sine squared of 2x. So let's make that substitution. So this is going to be 1/4 times the integral of sine squared of 2x dx. All right. Once we're there, we can go ahead and use another one of our properties, which says that so we're going to be using the half angle identity here, which says that sine squared of 2x is equal to 1/2 times 1 minus cosine of 4x. Right, now this is not exactly what the half angle identity says. Right, our half angle identity says sine squared of x is equal to 1/2 times 1 minus cosine 2x. That's exactly what our half angle identity says. However, I like to think of this as sine squared of f of x is equal to 1/2 times 1 minus cosine of 2 f of x. Okay. And so if we replace that f of x with 2, that's why we get this 4x over here. So let me go ahead and use this. So we're going to have 1/4 times the integral. So we said that sine squared of 2x is going to be equal to 1/2 times 1 minus cosine 4x dx. So this is 1/8 times the integral of 1 minus cosine 4x dx. And then from here, we can just integrate. Right. The proper way to integrate from here is when we're integrating this part, cosine of 4x, we use u sub. So if you need to, go ahead and use that. If you've already gotten like really comfortable with how it works, then this is going to be 1/8 times, so the integral of 1 is going to be x. The integral of negative cosine of 4x, that's going to be negative 1/4 sine 4x. The way I'm doing that in my head is I know that I have to have negative sign because the derivative of negative sign gives me negative cosine. I know I have to have a 4x in here because I'm going to have a 4x in here. When I do chain rule on that, I'm going to multiply by 4 out front. Well, since I have technically like a 1 out front right there, I want to multiply this 4 by 1/4. So that's why I have that 1/4 right there. Okay. And then, of course, plus c. Okay. So this is going to be our answer to example number 5. And now we'll look at example number 6. So here again, we'll get to practice a definite integral. All right, so on this problem, we'll again be using our half angle identity. So this is going to be the integral from negative pi to pi of 1/2 1 plus cosine 2x dx, which is equal to 1/2 times the integral from pi to negative pi of 1 plus cosine 2x dx. Right, so all I'm doing there is just pulling out our constant multiple 1/2. And then now I'm going to use u substitution on u equals 2x. So we'll get du over 2 equals dx. So we get 1/2 times the integral. So now I need to multiply my upper and lower limits by 2 because of this right here. So this becomes 2 pi, negative 2 pi. And then I should have 1 plus cosine u du. Right, and actually, so du is dx is equal to du over 2, so there should be a du over 2 right here. Here, what I'm doing is that u sub I was talking about on the last problem. So here I said if you need to use u sub right here, right, so this is similar to how it would look right here. I just wanted to go ahead and show the steps out. So this is going to be 1/4 times the integral from negative 2 pi to 2 pi of 1 plus cosine u du. Alright, so now we get 1/4 times, let's see, this is going to be u plus sine of u, evaluated from negative 2 pi to 2 pi. So this becomes 1/4 times 2 pi plus sine of 2 pi, which is 0, minus, we'll have minus negative 2 pi, so it's plus 2 pi, minus sine of negative 2 pi, which is 0. So this is 1/4 of 4 pi, which will give us pi as our answer. Right? So maybe the next time at Thanksgiving, you should ask somebody to make you some apple integral from negative pi to pi cosine squared of x dx. Right? In other words, ask them to make you some apple pie. Alright, now so for part 2, we're going to be looking at integrals that look like secant to some power times tan to some power. The first case we're going to look at is what happens if the power of tangent is odd. If the power of tangent is odd, then we are told to factor out a secant x of tan of x. So this becomes the integral of, so I'm factoring out a secant x tan x. So it should become tan squared of x secant squared of x times secant x tan x. Right, so we just write this unnecessarily long, right? Because when you write more stuff down on the paper, it looks like you're doing more. It looks more fancy. No. There's like an actual reason we're doing this. After we do this, we're going to use u substitution with u equal to secant of x. Okay? And so that's coming from this part right there. So now we're going to look at that u substitution. Okay? So if I use u equals secant of x, actually before I do that, I'm going to slide in a quick little identity. This quick little identity that I'm going to slide in is I'm going to try to make as many secant of x's in this problem as I can. Right? Remember in the last part, I said, okay, if you're using u equals cosine of x, get as many cosine of x's in there as you can. So change your sine squared of x to 1 minus cosine squared of x. So in this case, we're doing u equals secant of x. So I went as many secant of x's in here as I can get. So what that means is I need to change this tan squared of x right here to, let's see, this should be secant squared of x minus 1. Right, I'm using that identity. If you go all the way up to the top, you'll see one that says tan squared of x equals secant squared of x minus 1. Right, so I'm doing that. Then I get another secant squared of x right here. Right, so I can't make any more secants out of that. And then I have my secant x tan x dx. Right, so now I've made this even longer, which looks just even more impressive to broadcase our mathematical abilities. So now we'll use u equals secant of x, which means I'm going to write this out this once just so that we can see it clearly. So this means du dx is equal to secant x tan x. Dividing across by the right hand side and then multiplying across by dx, we'll get du over secant x tan x is equal to dx. Okay, let's make that substitution. So this becomes the integral of So u is equal to secant of x, so this is u squared minus 1 u squared times, now this part right here I am not going to mess with. The reason I'm not going to mess with is because it's going to cancel out and do all sorts of pretty stuff. So this dx right here, this becomes our du over secant x tan x, and now we should see why I didn't mess with this, why I left it there so we can cancel stuff out. Alright, because now this cancels with each other. And so then we're left with the integral of u squared minus 1 times u squared times du. So this becomes the integral of u to the 4th minus u squared du. And so integrating this, we get u to the 5th over 5 minus u cubed over 3 plus c. And then we just input u equals secant of x. So this is secant to the 5th of x over 5 minus secant cubed of x over 3 plus c. All right, and then there's our answer. Actually, just for someone, there we go. There's our answer. Hopefully y'all can see what color that is. It's our favorite. Okay. Now let's look at example 8. So example 8 looks a little bit different, right? It doesn't look like secant tangent, but it has the same general idea. If you scroll up, instead of seeing identities with secant squared and tan squared in it, you'll see an identity that has cotangent squared and cosecant squared. So this has a very similar structure to it, in that we're going to write this as cotangent to the 4th of x, cotangent of x. Right, I get myself an even power there. Then we have cosecant of x dx. And then what I use is I use u equals cosecant of x. So u equals cosecant of x, which means that negative du over cotangent x cosecant x is equal to dx. If you need to, go ahead and take that derivative on both sides of our u equals cosine of x, our u equals cosecant of x equation, and go ahead and verify that you get this right here. But because of the amount of years that I've just spent loving mathematics, I was able to kind of see this. So now we can rewrite our integral as the integral of, so the first thing I'm going to do is I'm going to notice that cotangent to the 4th of x is the same thing as cotangent squared of x squared. Okay, and then now I'm going to use our identity for cotangent squared of x. So this is cotangent squared of x is the same thing as cosecant squared of x minus 1. And we square this, right? Because this is technically cotangent squared of x squared, so that we get that power of 4. And then we'll have our cotangent of x, and then our cosecant of x dx. Now I'm going to apply our u sub, right? And so what I notice down here is when I plug in for dx, I have this cotangent x cosecant x. So I'm not going to mess with this part right here. However, what I am going to do is change this cosecant squared of x right here to our u squared. So this is u squared minus 1 squared. Actually, let me go ahead and write this out. Okay. So this turns into u squared minus 1 squared cotangent x cosecant x And then dx is the same thing as negative du over cotangent x cosecant x. Alright, so these cancel. And then we're left with the integral of u squared minus 1 squared. And then I have to remember this negative sign right here, so I'm going to pull this out here. Okay. And so then this becomes the negative integral of u to the fourth plus 1 minus 2u squared du. And so then this is negative u to the fifth over 5 minus u plus 2u cubed over 3. So this is negative cosecant to the fifth of x over 5 minus cosecant x plus 2 cosecant cubed of x over 3 plus c. And I welcome you to go ahead and take the derivative of that and prove that it's really equal to this up here. Or you can believe me. Don't know which one is more fun. Okay, now let's move on to our other possibility. So the first one we looked at said that n was an odd power, and let's just go ahead and remember n was our power for tangent. So now we're going to look at if m is even, meaning what happens if secant has an even power. And just like in our other part, if you have secant has an even power and tangent has an odd power, then you can use either one of these. Okay? So here we have secant with an even power. And so what it says to do is it says to factor out a secant squared of x. Okay, before I do that, I notice that this isn't just x in here. This is an x squared. So what I want to do is go ahead and do a u sub, because that'll cancel out this x in front. Okay. So let's go ahead and do a w sub. So we'll do u sub, because I don't think we have to use any u's for like integration by parts or anything else here. So we'll get du over 2x equals dx. So this becomes the integral of x tan to the fourth of u secant to the fourth of u du over 2x. So this is 1/2 times the integral. Remember our x's here cancel. Let's make that look less awful. There we go. So the x's cancel, and we'll just have our tan to the fourth of u secant to the fourth of u du. Now we factor out that secant squared. So now we have 1/2 tan to the fourth of u secant squared of u secant squared of u du. Now, here it says use u substitution, right? So we factor out that secant squared of x. Then it says use u substitution with u equals tan of x. So we'll use w substitution. So we'll have w equals tan of u, which means that dw over secant squared of u equals du. So what I notice here is that when I plug in for this du right here, this secant squared can cancel out with one of these. However, another secant squared will still be left there. So what I'm going to do is change this secant squared using the tangent identity. Sorry for going off on the brief little tangent there. But I really did believe that it was kind of like parallel to the stuff that we were already doing. So this is 1/2 times the integral. let's see, this should be w to the fourth of u. Secant squared of u, that would be the same thing as 1 plus tan squared of u. But remember, tan is just w, so this is going to be 1 plus w squared. Oh, and that's not w to the fourth of u, that's just, okay. Tan to the fourth of u, that's w to the fourth. Secant squared of u is the same thing as 1 plus tan squared of u. And tangent of u is w, so this is 1 plus w squared. And then we leave this secant squared alone. We plug in for du, so we get dw over secant squared of u. These cancel. And so our integral will become 1/2 the integral w to the fourth 1 plus w squared dw. So then multiplying out this w to the fourth, we'll get 1/2 the integral of w to the fourth plus w to the sixth dw. I really want to throw like an F in there, that way it says DFW. It's like Dallas Fort Worth or something like that. I don't know, it just like keeps on popping up in my head. Maybe I'll figure out a way to do it this semester. So then this will be, once we integrate, this is going to be w to the fifth over 5 plus w to the seventh over 7 plus c. Okay, so w is tangent of u. So this is 1/2. Actually, I'm going to go ahead and multiply this out. So this is going to be tangent to the fifth of u over 10, because of the 2 times 5, plus, what an amazing plus mark, tangent to the seventh of u over 7 times 2, which is 14, plus c. Okay, so then now we have to plug in for u. U is equal to x squared. So this is tangent to the fifth of x squared over 10 plus tangent to the seventh of x squared over 14 plus c. Okay, and there's our answer. Okay, and then for our final problem, we're going to look at a case where we have tangent has an odd power and secant has an even power, which means that we can use either of the two methods above. Now, one of these methods is going to be a lot easier than the other. But of course we'll do both, because it wouldn't be fun if we just did the easier one. So here we'll have method 1, and here we'll have method 2. Alright, so method 1 is going to be where we factor out the secant x tan of x. Alright, so we'll have, this is equal to the integral tangent to the 8th of x secant cubed of x secant x tan x dx. I have no idea what just happened there. Yikes. There we go. Okay. Then remember, the goal after this was to try to change as many things into secants as possible. So this becomes, let's see. So we can write that as tan squared to the fourth to get our tan to the 8th. But tan squared is the same thing as secant squared minus 1. So this is secant squared of x minus 1 to the 4th power. Secant cubed of x. Secant x tan x, because remember, we don't mess with that part. And then after we've done this, this is where we do our u sub. So we do u equals secant of x, which means that du over secant x tan x is equal to dx. So then this becomes the integral of u squared minus 1 to the 4th u cubed secant x tan x, and then this is du over secant x tan x. I don't like the way that's written. Try again. Secant x tan x. So these will cancel, and we'll be left with the integral from u squared minus 1 to the 4th u cubed du. Now, this is totally solvable. One way to go at it is that we just FOIL out u squared minus 1 over and over again until we've hit the 4th power. Then we distribute the u cubed across everything. Then we do a gigantic power rule. Won't be too bad. We're just adding 1 to exponents and dividing. Then we plug it back in for u, and we'll get this big, long, nasty thing. Okay. The other option is that we all know the binomial theorem off the top of our heads. So we're able to easily rewrite this, and then we distribute that u cubed and integrate. I don't think either of these are fun. I also don't think that statement about all of us having the binomial theorem memorized off the top of our heads is true. Okay? So, instead, what I propose is that we sit back and enjoy method 2. Method 2 is where we factor out the secant squared of x. So, we change our integral, so this will be tan to the 9th of x. Tan to the 9th of x. And we get secant squared of x, secant squared of x, dx. And then we have, so we try to change as many of these into tangents as we can, except for we leave one of these alone. So this becomes tangent to the 9th of x. Remember, secant squared is equal to 1 plus tangent squared. So this is 1 plus tan squared of x, secant squared of x, dx. Now we use the u sub of u equals tan of x, of u equals tan of x, which means du over secant squared of x is equal to dx. So this is the integral of u to the 9th times 1 plus u squared times secant squared of x times du over secant squared of x. These guys cancel. And we get the integral of u to the 9th, 1 plus u squared, du. We distribute out this u to the 9th. So we get the integral of u to the 9th plus u to the 11th du, which will give us u to the 10th over 10 plus u to the 12th over 12 plus c, which is going to be equal to tangent to the 10th of x over 10 plus tangent to the 12th of x over 12 plus c. Okay. That will finish off this 7.2 lecture. This is now the cutoff. This is where you can stop. You've now watched all the material that's going to be required for Wednesday's class activity. Right? You've now also covered all of the material that's going to be required for the exam on Friday.